Welcome to the Routing Fundamentals module, which explains the basic routing operations and concepts. The module explains how to view and describe routing and forwarding tables, configure and monitor static routing, OSPF, interfaces, and routing for IPv6. Routing is the process of moving data between Layer 3 or L3 networks. Routers are the most common devices for performing routing operations. However, many switches and security devices also perform routing operations. At the end of this module, you will be able to explain basic routing operations and concepts, view and describe routing and forwarding tables, configure and monitor static routing, configure and monitor OSPF, configure interfaces and routing for IPv6. Routing, in its most basic form, is the process of moving data between Layer 3 networks. The sample topology displayed on the screen consists of several Layer 3 networks, all connected to routers. Although routers are the most common devices for performing routing operations, note that many switches and security devices also perform routing operations. Note also that the Internet is a collection of many networks rather than a single network. It is essential to look at the required components of routing and how devices running the Junos OS make routing decisions. You must consider several components and other aspects to effectively implement routing between remote networks. However, you can classify the various components and considerations into two primary requirements. One requirement is to have an end-to-end communication path, and the other requirement is to ensure that all Layer 3 devices within the communication path have the required routing information. Click each requirement to learn more. For the first requirement, in the example shown, you can see that a physical path exists between the highlighted networks and the Internet. As long as the physical path is configured and is functioning correctly, the end-to-end communication requirement is satisfied. For the second requirement, all Layer 3 devices participating in the communications path must have the necessary routing information. The devices within the user and data center networks must have the proper gateway configured, which is a router that connects to those networks as well as to the Internet. The gateway device must determine the proper next hop for each destination prefix for transit traffic it receives. Devices running the Junos OS use the forwarding table, which is a subset of information found in the routing table, to make this determination. Routing and forwarding tables will be discussed in the following sections. Consider the simple routing scenario displayed on the screen. In this scenario, what routing information is required for user A to communicate with a device in the data center network? For any device to communicate with another device outside its directly connected subnet, a properly configured gateway is required. In this scenario, the device associated with user A must have its gateway set to the router's IP address 10.1.1.1. Likewise, the devices within the data center network need a properly configured gateway 10.2.2.1. The router, which functions as the gateway device for the user and data center networks, requires sufficient routing information to determine the proper next hop for the traffic sent between the connected networks. In this example, the router learns the required information by way of the interface configuration. The router adds the networks, in which the interfaces are participating, to the routing and forwarding tables. The router consults its forwarding table to determine the actual next hop for received traffic. The Junos OS routing tables consolidate prefixes from multiple routing information sources, including various routing protocols, static routes, and directly connected routes. When a device running the Junos OS receives multiple routes for a given prefix, it selects a single route as the active route. With additional configuration, the Junos OS supports multiple equal-cost routes. The router uses the active route for each destination prefix to populate the forwarding table. The forwarding table determines the outgoing interface and Layer 2 read-write information for each packet forwarded by a device running the Junos OS. Devices running the Junos OS can accommodate multiple routing tables. The primary routing table, inet.0, stores IPv4 unicast routes. Additional predefined routing tables exist, such as INET 6.0, which the Junos OS creates when the configuration requires it. An administrator can create custom routing tables to be used in addition to these routing tables. Click the Additional Information button to view the summary of the common predefined routing tables. The Junos OS uses route preference to differentiate routes received from different routing protocols or routing information sources. Route preference is equivalent to administrative distance on equipment from other vendors. The Junos OS uses route preference to rank routes received through the various route information sources and as the primary criterion for selecting the active route. The table shows the default preference values for a selected set of routing information sources. The table displayed shows the default preference values for routing information sources. Routing preference values can range from 0 to 4,294,967,295. Lower preference values are preferred over higher preference values. The displayed command output demonstrates that a static route with a preference of 5 is preferred over an OSPF internal route with a preference of 10. You can modify the default preference value for most routing information sources to make them more or less desirable. The exception is with the direct and local routes, which are always preferred, regardless of the modified route preference value associated with other routing information sources. If equal cost paths exist for the same destination, the Routing Protocol Daemon, or RPD, randomly selects one of the available paths. This approach provides load distribution among the paths while maintaining packet ordering per destination. The displayed output illustrates this point. Note: if desired, you can enable per-flow load balancing over multiple equal cost paths through routing policy. Load balancing is outside the scope of this module. The example shows the use of the Show Route command, which displays all route entries in the routing table. As identified in the example, all active routes are marked with an asterisk next to the selected entry. Each route entry displays the source from which the device learned the route, along with the route preference for that source. The Show Route command displays a summary of active, hold down, and hidden routes. Active routes are the routes the system uses to forward traffic. Hold down routes are routes that are in a pending state before the system declares them as inactive. Hidden routes are routes that the system cannot use for reasons such as an invalid next hop and route policy. You can filter the generated output by destination prefix, protocol type, and other distinguishing attributes. The displayed sample capture illustrates the use of the protocol filtering option. The forwarding table stores a subset of information from the routing table. Within the forwarding table, you can find the details used by a device running the Junos OS to forward packets, such as the learned destination prefixes and the outgoing interfaces associated with each destination prefix. You use the Show Route Forwarding Table (CLI) command to view the forwarding table contents. Note that the Junos kernel adds some forwarding entries and considers them permanent in nature. One such example is the default forwarding entry, which matches all packets when no other matching entry exists. When a packet matches this default forwarding entry, the router discards the packet and it sends an Internet Control Message Protocol, or ICMP destination unreachable message, back to the sender. If you configured a user-defined default route, the router uses it instead of the permanent default forwarding entry. Click the Additional Information button to view the common route types and next hop types associated with forwarding entries. When a packet enters a device running the Junos OS, it compares that packet against the entries within the forwarding table to determine the proper next hop. If the packet is destined to the local device, the Junos OS processes the packet locally. If the packet is destined to a remote device and a valid entry exists, the device running the Junos OS forwards the packet out the next hop interface associated with the forwarding table entry. If multiple destination prefixes match the packet's destination, the Junos OS uses the most specific entry, which is also called longest match, when forwarding the packet to its destination. In situations where no matching entry exists, the device running the Junos OS responds to the source device with a destination unreachable notification. The example displays a sample forwarding table and tests your understanding of how next hop interfaces are determined. Although multiple entries might match a destination, the device uses the most specific longest match entry when determining a packet's next hop interface. The most specific forwarding entry matching packets destined to 172.19.52.101 is the 172.19.52.0/24 destination prefix. The next hop associated with this destination prefix is GE0/0/1.0. The most specific forwarding entry matching packets destined to 172.19.52.21 is the 172.19.52.16/28 destination prefix. The next hop associated with this destination prefix is GE0/0/2.0. The only forwarding entry matching packets destined to 172.25.100.27 is the user-defined default forwarding entry. The next hop associated with the user-defined default forwarding entry is GE0/0/0.0. The Junos OS logically groups routing tables, interfaces, and routing protocol parameters to form unique routing instances. The device logically keeps the routing information in one routing instance apart from all other routing instances. The use of routing instances introduces great flexibility because a single device can effectively imitate multiple devices. The Junos OS creates a default unicast routing instance called the master routing instance. By default, the master routing instance includes the inet.0 routing table, which the device uses for IPv4 unicast routing. The software creates other routing tables, such as inet6.0, adds them to their respective routing instance, and displays them when required by the configuration. The Junos OS also creates private routing instances, which the device uses for internal communications between hardware components. You can safely ignore these instances and their related information when planning your network. Click the Additional Information button to view a sample output, which shows all default routing instances. For added flexibility, the Junos OS allows you to configure additional routing instances under the Edit Routing Instances hierarchy. You can use user-defined routing instances for a variety of different situations, which provides you a great amount of flexibility in your environments. Some typical uses of user-defined routing instances include filter-based forwarding, or FBF, Layer 2 and Layer 3 VPN services, and system virtualization. Let's take a look at some of the common routing instance types. Forwarding is used to implement filter-based forwarding for common access layer applications. L2 VPN is used in Layer 2 VPN implementations. No forwarding is used to separate large networks into smaller administrative entities. Virtual router is used for non-VPN related applications such as system virtualization. VPLS is used for point-to-multipoint LAN implementations between a set of sites in a VPN. VRF is used in Layer 3 VPN implementations. Note that the actual routing instance types vary between platforms running the Junos OS. Be sure to check the technical documentation for your specific product. The example illustrates basic routing instance configuration. Once you configure a routing instance and the device learns routing information within the instance, the Junos OS automatically generates a routing table. There are two key things to know when working with routing instances. 1. Reference the corresponding IP unicast table for a given instance to view the route table contents. 2. Reference the routing instance name when viewing information for a given instance or sourcing traffic from a given instance. Click each part to learn more. Static routes are used in a networking environment for multiple purposes, including a default route for the autonomous system, or AS, and as routes to customer networks. Unlike dynamic routing protocols, you manually configure the routing information provided by static routes on each router or multi-layer switch in the network. All configuration for static routes occurs at the Edit Routing Options level of the hierarchy. Static routes must have a valid next hop defined. Often, that next hop value is the IP address of the neighboring router headed toward the ultimate destination. On point-to-point interfaces, you can specify the egress interface name rather than the IP address of the remote device. Another possibility is that the next hop value is the bit bucket. This phrase is analogous to dropping the packet off the network. Within the Junos OS, the dropping of packets is represented with the keywords reject or discard. Both options drop the packet from the network. The difference between them is in the action the device running the Junos OS takes after the drop action. If you specify reject as the next hop value, the system sends an ICMP message or the network unreachable message back to the source of the IP packet. If you specify discard as the next hop value, the system does not send back an ICMP message. The system drops the packet silently. By default, the next hop IP address of static routes configured in the Junos OS must be reachable using a direct route. Unlike routing software from other vendors, the Junos OS does not perform recursive lookups of next hops by default. Static routes remain in the routing table until you remove them or until they become inactive. One possible scenario in which a static route becomes inactive is when the IP address used as the next hop becomes unreachable. The basic configuration syntax for IPv4 and IPv6 static routes is displayed. The No Re-advertise option prohibits the redistribution of the associated route through routing policy into a dynamic routing protocol such as OSPF. It is recommended that you use the No Re-advertise option on static routes that direct traffic out the Management Ethernet interface and through the management network. Note that IPv6 support varies between Junos devices. Be sure to check the technical documentation for your specific product for support information. Static routing can be monitored by using the following verification steps. Use Show Route Protocol Static to display static routes. Use the Ping utility to verify end-to-end reachability. By default, the Junos OS requires that the next hop IP address of static routes be reachable using a direct route. Unlike software from other vendors, the Junos OS does not perform recursive lookups of next hops by default. As illustrated, you can alter the default next hop resolution behavior using the Resolve CLI option. In addition to the Resolve CLI option, a route to the indirect next hop is also required. Indirect next hops can be resolved through another static route or through a dynamic routing protocol. It is recommended to use a dynamic routing protocol as your method of resolution whenever possible. Using a dynamic routing protocol rather than a static route to resolve indirect next hops dynamically removes the static route if the indirect next hop becomes unavailable. The Qualified Next Hop option enables independent preferences for static routes to the same destination. In the sample configuration shown, the 172.30.25.1 next hop assumes the default static route preference of 5, whereas the qualified 172.30.25.5 next hop uses the defined route preference of 7. All traffic using this static route uses the 172.30.25.1 next hop, unless it becomes unavailable. If the 172.30.25.1 next hop becomes unavailable, the device uses the 172.30.25.5 next hop. Some vendors refer to this implementation as a floating static route. Static routing is ideal in small networks, where only a few routes exist, or in networks where absolute control of routing is necessary. However, static routing has certain drawbacks that might make it cumbersome to manage in large environments, where growth and change are constant. For large networks, or networks that change regularly, dynamic routing might be the best option. With dynamic routing, you simply configure the network interfaces to participate in a routing protocol. Devices running routing protocols can dynamically learn routing information from each other. When a device adds or removes routing information for a participating device, all other devices automatically update. Dynamic routing resolves many of the limitations and drawbacks of static routing. Some of the general benefits of dynamic routing include lower administrative overhead, increased network availability, greater network scalability. Click each benefit to learn more. Let's summarize the key points related to dynamic routing protocols. Interior Gateway Protocols, or IGPs, operate within a single autonomous system. The single network administration provides unique routing policy and flexible use of network resources. Examples of IGPs include RIP, ISIS, and OSPF. Exterior Gateway Protocols, or EGPs, operate among different autonomous systems. In general, EGPs are used by independent administrative entities to communicate between independent network infrastructures. The current EGP that is used is BGP. OSPF is a link state routing protocol designed for use within an AS. OSPF is an IGP. Link state protocols allow for faster reconvergence, support larger internetworks, and are less susceptible to bad routing information than distance vector protocols. Devices running OSPF send out information about their network links and the state of those links to other routers in the AS. This information transmits reliably to all other routers in the AS by means of link state advertisements, or LSAs. The other routers receive this information, and each router stores it locally. This total set of information now contains all possible links in the network. In addition to flooding LSAs and discovering neighbors, another major task of the Link State Routing Protocol is establishing the Link State Database, or LSDB. The link state, or topological database, stores the LSAs as a series of records. The important information for the shortest path determination process is the advertising router's ID, its attached networks and neighboring routers, and the cost associated with those networks or neighbors. OSPF uses the shortest path first, or SPF algorithm, also called the Dijkstra algorithm, to calculate the shortest paths to all destinations. It performs this calculation by calculating a tree of shortest paths incrementally and picking the best candidate from that tree. OSPF uses areas to allow for a hierarchical organization and to facilitate scalability. An OSPF area is a logical group of routers. The software can summarize the routing information from an OSPF area, and the device can pass it to the rest of the network. Areas can reduce the size of the LSDB on an individual router. Each OSPF router maintains a separate LSDB for each area to which it is connected. The LSDB for a given area is identical for all participating routers within that area. To ensure correct routing knowledge and connectivity, OSPF maintains a special area called the backbone area. OSPF designates the backbone area as area 0.0.0.0. All other OSPF areas must connect to the backbone. All data traffic between OSPF areas must transit the backbone. Let's now look at a case study to understand how OSPF works. The displayed topology is used in this case study. The objective of the case study is to use a single OSPF area to provide connectivity among all connected subnets and loopback addresses, and to ensure that no adjacencies are formed on interfaces connecting to the 172.20.x.0/24 subnets. The displayed sample OSPF configuration for router A is used in this case study. Although not shown, router B and router C require a similar OSPF configuration to establish adjacencies and share routing information. To display adjacencies, use Show OSPF Neighbor. For added information, use Detail or Extensive options. In the sample output, you can see that Router A has formed adjacencies with both Router B and Router C. Click each field of the output to view its description. The screen illustrates the Show Route Protocol OSPF command, which displays OSPF routes learned by Router A. Note that Router A does not actually install its directly connected subnets in its route table as OSPF routes. It installs them as direct routes. IPv6 is already enabled on Juniper routers, so no global command is required. You must, however, configure IPv6 packet processing on an interface by adding Family INET 6. Enabling IPv6 on an interface automatically configures the interface's link local address and activates IPv6 processing for that interface. Additional addresses can be configured, and the link local address can be manually configured to override the automatically created address. As you can see from the displayed example, explicitly configuring an IPv6 address on an interface differs from configuring an IPv4 address only in that you use Family INET 6 and an IPv6 format address. Simply entering the configuration command set Family INET 6 will cause IPv6 packet processing to be enabled on the interface and a link local address to be generated. If you configure EUI64 addressing, the router will automatically generate an interface ID based on the interface's MAC address. For multi-access networks, /64 prefix lengths are most commonly used. For point-to-point links, many prefix lengths have been used, including /64, /124, and /126. But current best practice according to RFC 6164 is to use /127 prefix length. Note: details of IPv6 addressing architecture are beyond the scope of this course. Refer to RFC 4921 and its updates for further information. IPv6 static routes are conceptually identical to IPv4 static routes. Configuration in the Junos OS is also similar for IPv4 and IPv6. As with IPv4, IPv6 static routes are configured at the routing options hierarchy level. The only difference is that for IPv6, you need to specify the IPv6 RIB, which by default is INET 6.0. As shown in the example, a link local address may be used as the next hop for an IPv6 static route, but the outgoing interface must also be specified, since link local addresses are not globally unique. OSPF version 3, or just OSPF, for IPv6 is defined in RFC 5340 with some additional features such as graceful restart and authentication defined on separate documents such as RFC 5781, OSPF v3, graceful restart, and RFC 4552, authentication or confidentiality for OSPF v3. OSPF v3 maintains the fundamental mechanisms of OSPF, including LSA flooding scopes, areas, DR election, stub areas, not so stubby areas, or NSSAs, and so on. However, some changes are necessary to account for the differences in IPv4 versus IPv6 addressing. Notwithstanding the differences under the covers, for you to configure OSPF v3 on the Junos OS, all you need to do is replace OSPF with OSPF 3 in your configuration commands.
Welcome to the lab section of the module. This lab demonstrates tasks using both the CLI and the JWeb interfaces. Click this button to view a guided demonstration of the tasks performed in the Junos OS CLI interface. Click this button to view a guided demonstration of the tasks performed in the Junos OS JWeb interface. Welcome to the Junos OS CLI lab. This lab demonstrates configuration and monitoring of Layer 3 routing on devices running Junos OS. In this lab, you use the CLI to configure and monitor interfaces, static routing, and basic OSPF. Throughout these configuration tasks, you become familiar with and describe the contents of the routing and forwarding tables. At the end of this lab, you will be able to configure and verify proper operation of network interfaces, configure and monitor static routing, configure and monitor OSPF. Click Continue to begin the lab. This lab consists of 5 parts. Click each part to view its guided demonstration. Part 1. Configuring and monitoring interfaces. In this lab part, you configure network interfaces on your assigned device. You then verify that the interfaces are operational and that the system adds the corresponding route table entries for the configured interfaces. Confirm the device you have been assigned. Refer to the management network diagram to determine the management address of the student devices. Access the CLI of the VSRX1 device using either the console or the SSH. Log in to VSRX1 with lab as the username and lab123 as the password. Note that both the username and the password are case sensitive. Issue the configure command to enter the configuration mode and load the configuration file for the start of this lab using the load override ijos/lab 5 start.config command. After the configuration has been loaded, commit the changes and return to the operational mode using the commit and quit command. Issue the show route command to display the contents of the route table. Then, issue the show route all command to view all route tables and their respective entries. Enter the configuration mode and navigate to the Edit Interfaces hierarchy level. Refer to the management network diagram and configure the interfaces VSRX1. Use logical unit 0 for all interfaces. Remember to configure the loopback interface. Display the interface configuration and ensure that it matches the details outlined on the lab network diagram for this lab. Once you verify the interface configuration, issue the commit and quit command to activate the configuration and return to the operational mode. Issue the show interfaces terse command to verify the current state of the recently configured interfaces. Issue the show route command to view the current route entries. Use the ping utility to verify reachability to the neighboring router and virtual routers connected to the device. The output shows ping tests from VSRX1 to the Internet Gateway, VSRX2, and VR101, which are all directly connected. Part 2. Configuring and monitoring IPv6 interfaces. In this lab part, you assign IPv6 addresses to some interfaces and check for IPv6 connectivity. On the VSRX1 CLI session, enter the configuration mode and assign IPv6 addresses to LO0.0, GE0/0/1.0, and GE0/0/2.0, as per the lab network diagram. Display the interface configuration and satisfy yourself that it conforms with the lab network diagram. Commit the configuration and return to the operational mode. Using the ping and show interfaces terse commands, verify that the IPv6 interfaces are up and operational. Check IPv6 connectivity to the VSRX2 device using the ping command. Refer to the lab network diagram for the addresses. Using the VSRX1 CLI session, enter the configuration mode and issue the show security command. Enter the edit security hierarchy level and set forwarding options to forward family INET6 traffic in packet mode, as with the existing configuration for MPLS IPv4 traffic. Display the resulting configuration, commit the changes, and exit to the operational mode. Once again, test reachability of VSRX2 from VSRX1 using the ping command. Part 3. Configuring and monitoring static routing. In this lab part, you configure and monitor static routing. Attempt to ping the internet host shown on the lab network diagram for this lab. Define a default static route. Use the IP address identified in the last step as the next hop for the default static route. Commit the configuration when complete. Issue the run show route 172.31.15.1 command. Issue the run ping 172.31.15.1 rapid count 25 command to ping the internet host. Add a static route to the loopback address of the VR101 virtual router. Define the required static routes to enable end-to-end connectivity to the loopback addresses and link interfaces of VSRX2 and the VR102 virtual router. Use the IP address assigned to VSRX2 on the 172.20.66.0/30 subnet as the next hop for these static routes. Display the resultant static route configuration using the show command. Use the IP address assigned to VSRX2 on the 172.20.77.0/30 subnet as a qualified next hop for the recently added static routes to the remote subnet and loopback addresses. Use a route preference of 6 for these definitions. View the configuration using the show command. After the configuration is loaded, commit the configuration and return to the operational mode. Issue the show route protocol static command to view the current static routes in the device's route table. Ping the loopback address of all internal devices to verify reachability. Configure an IPv6 static route for the loopback address of VSRX2. Examine the resulting configuration and then commit and exit to the operational mode. Use the show route and ping commands to verify that the IPv6 static route is active in the inet6.0 routing table and that it provides connectivity to the loopback address of VSRX2. Part 4. Configuring and monitoring OSPF. In this lab part, you configure and monitor OSPF. Then, you configure a single OSPF area based on the lab network diagram. Finally, you perform some verification tasks to ensure that OSPF works correctly. Using the VSRX1 CLI session, navigate to the Edit Protocol's OSPF hierarchy level. Define OSPF Area 0 and include all internal interfaces that connect to VSRX2 and the directly connected VR101 virtual router. Ensure that you also include the LO0 interface. Issue the show command to view the resulting configuration. Activate the candidate configuration using the commit command. Issue the run show OSPF neighbor command to verify OSPF neighbor adjacency state information. Issue the run show route protocol OSPF to view the active OSPF routes in the device's route table. Delete all static routes used for internal connectivity. Ensure that you do not delete the default static route used to route traffic to the internet. Activate the configuration and return to the operational mode. Issue the show route protocol OSPF command to verify that the OSPF routes are now active. Ping the loopback address of all internal devices to verify reachability through the OSPF routes. Part 5. Configuring OSPF v3 for IPv6. In this lab part, you configure OSPF v3 for IPv6. Navigate to the Edit Protocol's OSPF3 hierarchy and add the interfaces for which you defined IPv6 addresses earlier. Activate the configuration and exit to the operational mode. Use the show OSPF3 neighbor command to verify that adjacencies have formed across the 2 gigabit Ethernet interfaces. Use the show route protocol OSPF3 command to see what routes have been received using the OSPF-v3 protocol. Use the show route FDA9::2 command to verify that it is indeed the static route taking preference from the OSPF-v3 route. Enter the configuration mode and delete all IPv6 static routes. Check the configuration, then activate the configuration and return to the operational mode. Use the show route FDA9::2 command again to show that the OSPF-v3 route is now active for that destination. Use the ping command to verify reachability. Log out of the CLI session to VSRX1 by issuing the exit command. Welcome to the Junos OS JWeb Lab. This lab demonstrates configuration and monitoring of Layer 3 routing on devices running Junos OS. In this lab, you use the JWeb interface, as well as the CLI to configure and monitor interfaces, static routing, and basic OSPF. This lab also describes the contents of the routing and forwarding tables throughout these configuration tasks and makes you become familiar with them. You can perform these configuration tasks for IPv4 and IPv6. At the end of this lab, you will be able to configure and verify proper operation of network interfaces, configure and monitor static routing, configure and monitor OSPF. Click Continue to begin the lab. This lab consists of 5 parts. Click each part to view its guided demonstration. Part 1. Configuring and monitoring interfaces. In this lab part, you configure network interfaces on the assigned device. You then verify that the interfaces are operational and that the system adds the corresponding route table entries for the configured interfaces. Access the CLI of the VSRX1 device using either the console or SSH. Log in to the VSRX1 with lab as the username and lab123 as the password. Note that both the username and the password are case-sensitive. Issue the configure command to enter the configuration mode and load the start configuration file for this lab using the load override ijos/lab5 start.config command. After the configuration has been loaded, commit the changes and return to the operational mode using the commit and quit command. Open a web browser on the student desktop. Navigate to https://172.25.11.1. Log in with lab as the username and lab123 as the password, and click Login. 5. Navigate to Monitor, Routing, Route Information. Examine the active routes. 6. Return to the CLI session you opened previously to the VSRX1 device and create a logical interface Unit 0 on the loopback interface LO0. Assign the IP address shown in the lab network diagram for the VSRX1 loopback. 7. Return to the JWeb session. Navigate to Configure Interfaces Ports. Refer to the lab network diagram and configure the interfaces for VSRX1. Use logical Unit 0 for all interfaces. Remember, you already configured the loopback interface in the previous step. You can perform these actions by completing the following sub-steps. Select the GE0/0/1 interface and add a new logical interface. Specify 0 as the unit and select the IPv4 address DHCP configuration checkbox. Click the Add button to configure the IP address. Configure the 172.20.77.1/30 IP address and click OK. Refer to the lab network diagram and repeat substeps 1 through 4 for the GE0/0/2, GE0/0/3, and GE0/0/4 interfaces. 8. Select the Compare option to verify that the interfaces have been configured. Once you have verified that the interfaces are configured correctly, select Commit. You can perform these actions by completing the following sub-steps. In the Actions list, select Compare. Verify that the interfaces are configured correctly and click Close. Click Commit. 9. Verify that the interfaces configured previously have a link state of Up. Filter the interfaces based on interface state and link up. Then, click Go. Navigate to Monitor, Routing, Route Information to view the current route entries. 11. Navigate to Administration, Tools, Ping Host. Use the Ping utility to verify reachability to the neighboring router and virtual routers connected to the device, which means you can start ping tests from VSRX1 to the Internet Gateway, VSRX2, and VR101, which are all directly connected. You can perform these actions by completing the following sub-steps. Click Start to ping 172.18.1.1. Click OK when the test has completed. Click Start to ping 172.20.66.2. Click OK when the test is completed. Click Start to ping 172.20.77.2. Click OK when the test is completed. Click Start to ping 172.20.101.10. Click OK when the test is completed. Part 2. Configuring and monitoring IPv6 interfaces. In this lab part, you assign IPv6 addresses to some interfaces and check for IPv6 connectivity. 1. Navigate to Configure, Interfaces, Ports, and assign IPv6 addresses to GE0/0/1.0 and GE0/0/2.0 as per the lab network diagram. You can perform these actions by completing the following sub-steps. Navigate to Configure, Interfaces, Ports. Select the GE0/0/1.0 interface and click the Edit button. Click the IPv6 address tab, then select the IPv6 address/DHP configuration checkbox and click the Add button. Configure FDA1:1/126 as the IP address and click OK. Repeat substeps 2 through 4 to add FDA2:1/126 as the IPv6 address for the GE0/0/2 interface. Commit the changes using the Commit option. Switch to the CLI of VSRX1. Configure FDA9:1/128 as the IPv6 address on the LO0.0 interface. Commit the changes and exit to the operational mode. Switch to the Web UI session for VSRX1. View the interface configuration and verify that it conforms with the lab network diagram. If you find any typos or misconfigured interfaces, be sure to fix them and recommit the changes. Also, verify that the interfaces have a link status of Up. Navigate to Administration, Tools, Ping Host. Using the ping commands, verify that the IPv6 interfaces are up and operational. You can perform this action by completing the following sub-steps. Enter the address and click Start to ping FDA9:1. Click OK when the test is completed. Enter the address and click Start to ping FDA1:1. Click OK when the test is completed. Enter the address and click Start to ping FDA2:1. Click OK when the test is completed. 6. Now check IPv6 connectivity to the VSRX2 device using the ping utility. Refer to the lab network diagram for the addresses. You can perform this action by completing the following substeps. Ping FDA1::2. Click OK when the test is completed. Ping FDA2::2. Click OK when the test is completed. Navigate to Configure, Network, Forwarding Mode. Select Packet-Based in the Family IPv6 field. Click Save. Commit the changes. 9. Navigate to Administration, Tools, Ping Host. Once again, test IPv6 reachability to VSRX2 from VSRX1 using the ping utility. You can perform this action by completing the following substeps. Click Start to ping FDA1::2. Click OK when the test is completed. Click Start to ping FDA2::2. Click OK when the test is completed. Part 3. Configuring and monitoring static routing. Part 3. Configuring and monitoring static routing. In this lab part, you configure and monitor static routing. 1. Ensure that you are in the ping host page. Attempt to ping the internet host as shown in the lab network diagram. Ping 172.31.15.1. Click OK when the test is completed. Navigate to Configure, Network, Routing, Static Routing. Define a default static route. Use the IP address identified in the last step as the next hop for the default static route. Commit the configuration when you complete. You can perform this action by completing the following substeps. Click the Add icon. Define the static route 0.0.0.0 as the IP address and the subnet mask. In the Next Hop section, click the Add button. Define the next hop IP address as 172.18.1.1 and click OK. Then, click OK in the Add Static Route page. Commit the changes. Navigate to Monitor, Routing, Route Information. Filter the route based on the internet host as the destination. You can perform this action by completing the following substeps. Filter the route based on the destination address. 172.31.15.1 and click Search. Examine the results. 4. Navigate to Administration, Tools, Ping Host. Attempt to ping the internet host again. Navigate to Configure Network Routing Static Routing. Add a static route to the loopback address of the VR101 virtual router. You can perform this action by completing the following substeps. Click the Add button at the top. Define the static route 192.168.1.2 as the IP address and 255.255.255.255/32 as the subnet mask. In the Next Hop field, click the Add button. Define the next hop IP address as 172.20.1.01.10 and click OK. Finally, click OK in the Add Static Route page. 6. Repeat the previous step to define the required static routes to allow end-to-end connectivity to the loopback addresses and link interfaces of VSRX2 and the VR102 virtual router. Use the IP address assigned to VSRX2 on the 172.20.66.0/30 subnet as the next hop for these static routes. Seven. Switch to the CLI of VSRX1. Use the IP address assigned to VSRX2 on the 172.20.77.0/30 subnet as a qualified next hop for the recently added static routes to the remote subnet and loopback addresses. Use a route preference of 6 for these definitions. Verify that the configuration is correct, and when satisfied, commit the configuration and return to the operational mode. Eight. Switch to the web UI of VSRX1. Navigate to Monitor, Routing, Route Information. View the current static routes in the device's route table by filtering routes based on the static protocol and click Search. 9. Navigate to Administration, Tools, Ping Host. Ping the loopback address of all internal devices to verify reachability. You can perform this action by completing the following substeps. Click Start to ping 192.168.1.2. When the test is completed, click OK. Click Start to ping 192.168.2.1. When the test is completed, click OK. Click Start to ping 192.168.2.2. When the test is completed, click OK. Navigate to Configure Network Routing Static Routing. Now configure an IPv6 static route for the loopback address of VSRX2. Examine the resulting configuration and then commit the configuration. You can perform this action by completing the following substeps. Click the Add button to add a new static route. Add the static route FDA9::2 as the IPv6 address and 128 as the prefix. Then, click the Add button to add the next hop gateway. Add the next hop gateway FDA1::2 as the IPv6 address and click OK. Use the Compare option to verify the configuration. Examine the changed configuration. Click Commit when you are finished. 11. Verify that the IPv6 static route is active in the INET 6.0 routing table and that it provides connectivity to the loopback address of VSRX2. You can perform this action by completing the following substeps. Navigate to Monitor, Routing, Route Information. Filter routes based on the INET 6.0 route table. Navigate to Administration, Tools, Ping Host. Ping FDA9::2 and click OK when the test is completed. Part 4. Configuring and Monitoring OSPF. In this lab part, you configure and monitor OSPF. You configure a single OSPF area based on the lab network diagram. Finally, you perform some verification tasks to ensure that OSPF works correctly. 1. Navigate to Configure Network Routing OSPF. Define OSPF Area 0 and include all internal interfaces that connect to VSRX2 and the directly connected VR101 virtual router. Ensure that you also include the LO0 interface. Commit the configuration when you complete. You can perform these actions by completing the following substeps. Click the Add icon to add a new OSPF area. Specify 0 as the area ID. Click Interface Details to open the tab. Select the displayed interfaces in the available section and click the arrow to move them to the selected section. Then click OK. Commit the configuration. Navigate to Monitor, Routing, OSPF Information. Verify OSPF Neighbor Adjacency State information. Navigate to Monitor, Routing, Route Information. Filter routes based on the OSPF protocol and click Search. Navigate to Configure, Network, Routing, Static Routing. Delete all IPv4 static routes used for internal connectivity. Ensure that you do not delete the default static route used to route traffic to the Internet. Commit the configuration. You can perform these actions by completing the following sub-steps. Select the displayed route and click the Delete button. Click Yes to confirm. Repeat substep 1 for the remaining IPv4 routes, except the default route. Commit the changes. 5. Navigate to Monitor, Routing, Route Information. Filter routes based on the OSPF protocol and click Search. 6. Navigate to Administration, Tools, Ping Host. Ping the loopback address of all internal devices to verify reachability through the OSPF routes. You can perform this action by completing the following substeps. Click Start to ping 192.168.1.2 and click OK when the test is completed. Click Start to ping 192.168.2.1 and click OK when the test is completed. Click Start to ping 192.168.2.2 and click OK when the test is completed. Part 5. Configuring OSPF v3 for IPv6. In this lab part, you configure OSPF v3 for IPv6. 1. OSPF v3 must be configured using the CLI. Switch to the CLI of the VSRX1 device. Navigate to the Edit Protocols OSPF3 hierarchy and add the interfaces for which you defined IPv6 addresses earlier, in the same way that you added interfaces when configuring OSPF. Activate the configuration and exit to the operational mode. 2. Use the Show OSPF3 Neighbor command to verify that adjacencies have formed across the 2 gigabit Ethernet interfaces. 3. Switch back to the JWeb interface of VSRX1. Navigate to Monitor, Routing, Route Information. Switch the route table to display INET 6.0 routes. Filter the protocol based on OSPF3 and click Search. Switch to the CLI of the VSRX1 device. Use the Show Route FDA 9::2 command to verify that it is indeed the static route taking preference from the OSPF v3 route. Switch to the web UI of VSRX1. Navigate to Configure, Network, Routing, Static Routing. Delete the static route and commit the configuration. You can perform this action by completing the following substeps. Select the IPv6 route and delete the route. Click Yes to confirm. Commit the changes. 6. Navigate to Monitor, Routing, Route Information. Switch the route table to display INET 6.0 routes. Specify OSPF3 for the protocol and click Search. Navigate to Administration, Tools, Ping Host. Click Start to ping FDA 9::2 and verify reachability. Log out of the Web UI session to VSRX1. 9. Log out of the CLI session to VSRX1 by issuing the Exit command.
You have reached the end of this module. In this module, you learn to explain basic routing operations and concepts, view and describe routing and forwarding tables, configure and monitor static routing, configure and monitor OSPF, configure interfaces and routing for IPv6.